Welcome to our guide on airborne radiation limits and stay time calculation. This video is designed for anyone working in or with environments where airborne radioactive materials are a concern. We will explore the critical concepts of derived air concentration, DAC, and maximum permissible concentration in air, MPCa, their relationship to annual limits, and how to accurately calculate stay times based on airborne concentrations. Understanding these principles is paramount for ensuring worker safety and compliance with radiation protection regulations. Airborne radiation limits are foundational to radiation safety. They define the maximum allowable concentrations of radioactive materials in the air that individuals can breathe without exceeding established dose limits. These limits are crucial for protecting workers from internal exposure, which can occur when radioactive particles are inhaled. Derived air concentration, or DAC, is a primary regulatory limit for airborne radioactivity. It represents the concentration of a given radionuclide in air that, if breathed for a standard working year, 2,000 hours, would result in an intake equal to one annual limit on intake, ALI. Essentially, it's the concentration you can safely breathe for a full year without exceeding a dose limit. Maximum permissible concentration in air, or MPCa, is an older but still relevant term, particularly in some international regulations and historical contexts. MPCa is similar to DAC in its purpose, also defining limits for airborne radioactive materials. Both DAC and MPCa aim to ensure that inhaled radioactive substances do not lead to an unacceptable radiation dose to internal organs. Both DAC and MPCa are directly derived from the annual limit on intake, or ALI. The ALI is the maximum amount of a specific radionuclide that can be taken into the body by an adult worker in a year without exceeding the annual dose limit for internal exposure. This annual limit considers the dose to all organs and the effective dose to the whole body. To derive DAC and MPCa from the ALI, regulatory bodies use complex dosimetric models. These models consider factors like the physical half-life of the radionuclide, its biological half-life, its absorption rate in the body, and the organs it irradiates. The derivation ensures that inhaling air at the DAC or MPCa limit for a set period will not result in exceeding the ALI. Adhering to DAC and MPCa limits is not just about compliance, it's about protecting health. Exceeding these limits can lead to significant internal radiation doses, increasing the risk of long-term health effects such as cancer. Regular monitoring and control measures are essential to keep airborne concentrations below these critical thresholds. Now let's move on to stay time calculation. When airborne radioactive material concentrations exceed DAC or MPCa, or are simply present, it becomes crucial to determine how long personnel can safely remain in that environment. Stay time is the maximum duration an individual can be present in an area with a known airborne concentration, without exceeding a predetermined dose or intake limit for that specific operation or shift. Understanding airborne concentration is the first step. This concentration is typically measured through air sampling, where air is drawn through a filter and the collected radioactive particles are then analyzed. The results are expressed in units of activity per unit volume, such as microcuries per milliliter or becquerels per cubic meter. The fundamental formula for calculating stay time is straightforward. Stay time equals the allowed intake divided by the airborne concentration. The allowed intake is typically a fraction of the ALI, tailored for the specific task or shift, ensuring that cumulative annual limits are not exceeded. For example, if a worker is allowed to receive 1/40th of an ALI per week, that value would be used. In practical application, if you have an area with an airborne concentration of 2 DAC and you're allowed to receive an intake equivalent to 0.5 DAC hours, then your stay time would be 0.5 DAC hours divided by 2 DAC, which gives you 0.25 hours, or 15 minutes. This calculation provides an immediate operational limit for personnel entry. Let's consider a few scenarios. If the airborne concentration is high, the stay time will be very short, emphasizing the need for robust respiratory protection and engineering controls like ventilation. Conversely, if concentrations are low, stay times can be extended, allowing for longer work periods. These calculations are dynamic and depend on real-time monitoring data. Several factors can affect stay time adjustments. These include the use of respiratory protection, which can significantly reduce the effective airborne concentration inhaled by the worker. Other factors include the specific task being performed, the presence of other radiation hazards, and any pre-existing exposure history of the individual. In conclusion, understanding DAC, MPCa, and stay time calculations is vital for maintaining a safe working environment when dealing with airborne radioactive materials. These tools empower radiation safety professionals to make informed decisions that protect personnel from internal radiation exposure. To recap, we defined DAC and MPCa as critical limits for airborne radioactivity, showed their derivation from annual limits, and emphasized the importance of staying within these boundaries. We then detailed the process of calculating stay time based on airborne concentrations, enabling safe operational planning. Always adhere to established safety protocols, utilize appropriate personal protective equipment, and ensure regular monitoring of airborne concentrations. Your safety and the safety of those around you depends on it. Thank you for watching. Feel free to reach out if you need further information. Nuvia is your lifecycle partner for highly regulated environments. We work to build a safer, cleaner, and more sustainable world.